There is a number written into the structure of reality, not a suggestion, not an engineering limitation. A fundamental boundary, approximately 299,792 kilometers per second, the speed of light in vacuum. It is not merely the speed of a particular thing. It is the maximum speed at which cause can influence effect. It is the edge of what is physically possible, but something extraordinary happens as you approach that edge. Common sense tells you that if you move faster, time simply passes the same way, but you cover more ground. Physics disagrees. As motion increases, time itself begins to deform. Clocks tick differently, duration stretches. The faster you go, the slower your internal processes unfold relative to someone at rest. This is not philosophy. It has been measured. Atomic clocks flown on airplanes return slightly out of sync with identical clocks left on the ground. Particles accelerated near the speed of light live longer than they should, according to ordinary expectations. Motion alters time. Push this idea further. Imagine accelerating closer and closer to the cosmic speed limit. 90% of light speed, 99%, 99.99%. Each step closer produces more dramatic time dilation. From the perspective of someone watching you, your clock ticks increasingly slowly. Now ask the sharper question. What happens at exactly the speed of light? Mathematically, time dilation becomes complete. The factor stretches toward infinity. For an object traveling at light speed, no time passes between departure and arrival. None. This is where intuition collapses. Imagine a photon emitted from the surface of a star billions of light, years away. From our perspective, it has been traveling across the expanding universe for billions of years before reaching a telescope on Earth. Galaxies moved, stars were born and died, civilizations rose and vanished, but along the photon's own path. The emission and the absorption are not separated by a ticking clock. They are connected by what physicists call a light-like interval, a path through spacetime with zero proper time. If you could ride alongside that photon, which you cannot, because no massive object can achieve its speed, you would not experience duration. There would be no journey in the way you imagine journeys, no stretching of moments. The beginning and the end would collapse into a single geometric connection. The fastest thing in the universe does not move through time the way you do. That fact alone should unsettle you. We tend to think of speed as something added on top of time, like distance divided by duration. But in relativity, speed is intertwined with the structure of space-time itself. Light does not merely travel through space. It traces the boundary of space-time. Its speed is not arbitrary. It is baked into the geometry of reality. Space-time can be pictured as a fabric with a particular structure that determines how intervals are measured. For ordinary objects moving slowly, time and space are separate components. You move through space at some rate, while time flows steadily forward. But as your velocity increases, the balance between space and time shifts. You trade spatial distance for temporal duration. The closer you approach light speed, the less proper time accumulates along your path. At light speed, the trade becomes absolute. All motion is spatial from an external perspective, but internally there is no elapsed time. This is not because light chooses to ignore time. It is because of how the geometry is constructed. The spacetime interval for light-like motion equals 0. The universe is configured so that light defines the slope of causality, the boundary between what can influence what. Visualize spacetime as a diagram. At each event there is a cone, a light cone, separating possible futures from unreachable regions. Everything that can be influenced by this event lies inside the future light cone. Everything that could have influenced it lies in the past light cone. The cone's surface represents paths taken by light. Those surfaces are where time, as experienced by massive objects, effectively disappears. Light does not sit inside the cone, it traces the boundary. This boundary role is crucial. Light is not simply another traveler moving through time. It defines the structure that makes time meaningful for everyone else. If causality depends on light's speed, and if at that speed duration vanishes, then time is not an independent universal backdrop. It is woven into the geometric relationships that light reveals. Think carefully about what this means. Time slows with motion. It slows with gravity, and at the ultimate velocity, it stops, at least in the sense of proper time along the path. This implies that time is relational, not absolute. The experience of duration depends on how you move through spacetime. Two observers following different trajectories will accumulate different amounts of proper time between the same pair of events. Twins separated by high speed travel will age differently. The universe does not enforce a single ticking rhythm. If time can stretch, compress, and vanish depending on motion, then it is not a fixed cosmic river. It behaves more like a dimension intertwined with space, responding to geometry and velocity. Now reflect on the paradox hidden here. You measure light's travel as taking years, centuries, millennia. Yet in its own frame, though strictly speaking light does not possess a rest frame, there is no temporal distance between emission and absorption. The entire span of cosmic history can collapse into a null interval along its path. The universe allows such a phenomenon. That suggests that what you call time passing is not a universal statement. It is a statement about your trajectory, about the path your mass takes through spacetime. Light reveals the fragility of time. We often think of time as inevitable, always advancing, impossible to escape. But light, which sits at the structural boundary of reality, experiences no such advancement. Its existence challenges the idea that duration is fundamental for all entities. Perhaps time is a property of massive objects moving below the cosmic speed limit, a feature emerging from the way matter interacts within spacetime. Light, massless and boundary, defining, is exempt, and if the fundamental constant of the universe leads to a regime where duration collapses, then time cannot be the ultimate ingredient. It must be derivative of something deeper, of geometry, of invariance, of relational structure. The speed limit of reality is not just a constraint on motion. It is the place where time begins to break. Imagine carrying a perfect clock in your hand. Not a mechanical one with gears and friction, but an atomic clock, vibrating with the precision of quantum transitions, measuring time with billions of oscillations per second. You stand still on the surface of Earth, and it ticks faithfully. Now step onto a spacecraft and accelerate to an enormous speed, faster than any ordinary object you have ever known. From your perspective inside the craft, the clock seems unchanged. It ticks normally. Your thoughts feel continuous. Your heartbeat remains steady, but someone watching you from Earth sees something radically different. Your clock is slow, not metaphorically slow, not perceptually slow, physically slow. Every second that passes for you corresponds to more than a second for the observer who remained behind. The faster you travel, the greater the discrepancy. Time does not merely measure motion, it responds to motion. This is the first fracture in the idea that time is universal. For centuries, it was believed that time flowed identically everywhere. The same second that passed in Paris passed in Beijing, on Earth and on Mars. Motion affected position, not duration. But experiments with high-speed particles demolished that certainty. Muons created in Earth's upper atmosphere should decay before reaching the surface. Yet they arrive in abundance because, from our perspective, their internal clocks run slowly due to their near-light velocities. Time dilation is not a trick of perception. It is built into the equations governing reality. Picture two identical twins. One remains on Earth, the other boards a spacecraft and travels at speeds near light before returning. The traveling twin does not feel anything unusual. The cabin feels ordinary. Meals are eaten. Conversations are held. The clock on the wall ticks calmly, yet when the traveler returns, less time has elapsed for them. Their body is younger. Their biological processes have unfolded more slowly. Time depends on trajectory. Now add gravity to this picture. Place one clock on Earth's surface and another in orbit. The clock deeper in Earth's gravitational field ticks more slowly. Even the GPS satellites circling the planet must account for this effect, or navigation systems would drift by kilometers each day. Gravity bends not only space, but time itself. The deeper you are in a gravitational well, the slower your time passes compared to someone far away. Motion slows time, gravity slows time. These are not two separate phenomena. They emerge from a unified structure called spacetime, a fabric in which space and time are inseparable components. Massive objects curve this fabric. Motion through this fabric alters how intervals are measured. Time is not a rigid metronome. It is flexible, malleable, responsive to geometry and velocity. Consider a thought experiment. Suspend two observers, one floating far from any gravitational influence, another hovering near an incredibly dense star. Both hold perfect clocks. The observer near the massive star experiences stronger curvature of spacetime. Their clock ticks slowly relative to the distant observer. From far away, the person near the star seems to move through molasses, like time. Yet to them, everything feels ordinary. Their own clock ticks normally relative to their heartbeat, their breathing, their thoughts. Here lies the unsettling realization: there is no universal now. Events that appear simultaneous to one observer may not be simultaneous to another moving at a different velocity. If two lightning bolts strike at either end of a moving train, a passenger inside may judge them simultaneous, while an observer standing on the platform insists one occurred first. Simultaneity is relative. This destroys the comforting notion of a single cosmic present shared by all observers. The present depends on your motion. When motion changes your measurement of time and your definition of simultaneity, time ceases to be an independent background. It becomes a coordinate intertwined with space and velocity. Mathematically, the quantity that remains invariant, unchanged across observers, is not time alone, nor space alone, but space-time interval. The geometry preserves a deeper relationship while allowing time and space to mix, depending on how you move. In this view, time dilation is not an anomaly. It is geometry in action. Visualize space-time as a four-dimensional landscape. Each object traces a world line through this landscape. The amount of time experienced by that object corresponds to the length of its path, not in ordinary Euclidean sense, but in space-time geometry. Different paths between the same two events can have different lengths. One twin's world line may involve rapid motion and curved trajectories, resulting in less accumulated proper time. The stay at home twin follows a straighter path through space-time and accumulates more time. The universe does not privilege stillness. It privileges geometry. This insight has profound implications. If time were absolute, it would flow identically regardless of motion or location. Instead, it behaves as a dimension woven into the structure of reality. Motion redistributes distance between spatial and temporal components. Increase your speed and more of your motion leans into spatial displacement, leaving less available for temporal advance. Gravity deepens this story. Massive bodies reshape space-time so dramatically that time itself slows in their vicinity. Near the edge of a black hole, this effect becomes extreme. To a distant observer, clocks near the event horizon appear nearly frozen. Time stretches under gravity the way rubber stretches under tension. What emerges is not chaos, but coherence. All observers, regardless of motion, agree on the laws of physics. They may disagree on durations and simultaneity, but they agree on invariant quantities. Reality maintains internal consistency through geometric symmetry. Time dilation reveals something deeper. Time is not fundamental in isolation. It is one aspect of spacetime's structure. Its rate of passage depends on how an object moves and where it resides within curvature. Imagine trying to define a universal second detached from motion and gravity. Physics refuses to allow it. Every clock measures its own proper time, the time along its world line. There is no master clock hovering outside the universe setting the pace. This destabilizes intuition. We experience time as steady because our daily velocities are tiny compared to light speed, and gravitational variations across Earth's surface are small. But scale up motion or gravity, and the illusion of uniform time dissolves. In high-energy particle accelerators, particles live longer because they move faster. In orbiting satellites, clocks tick at rates measurably different from those on Earth. The universe is quietly telling us that duration is contextual. If time bends with motion and gravity, then what we call flow may be a feature of our limited frame, a local description inside a much richer geometric structure. Motion rewrites duration not by breaking time, but by revealing that time was never rigid to begin with. Imagine standing far from a black hole, watching a star drift too close. The star crosses a boundary known as the event horizon, the point of no return. From your distant vantage point, something deeply strange unfolds. The star appears to slow down as it approaches that boundary. Its light becomes redder, dimmer, stretched. The closer it gets, the slower its clock appears to tick. Frame by frame, second by second, it seems to freeze. But here is the paradox: you never actually see it cross. From your perspective, the star asymptotically approaches the edge, fading, slowing, almost suspended in cosmic hesitation. It never quite disappears beyond the horizon. Its final light lingers indefinitely, stretched into invisibility by gravitational redshift. Time, as seen from far away, grinds nearly to a halt at the edge of the abyss. Now shift perspective. Imagine falling alongside that star. From this viewpoint, nothing dramatic occurs at the horizon itself. No barrier, no flash, no wall. The crossing happens in finite time. Your clock ticks normally. You fall through. Two realities emerge from one event. To the distant observer, time at the edge appears frozen. To the falling observer, time proceeds seamlessly. This is not contradiction. It is the nature of space-time curvature. A black hole is not simply an object in space. It is a region where space-time is curved so intensely that all future, directed paths inside the horizon lead inward. The geometry tilts so steeply that escape becomes impossible, not because of force in the ordinary sense, but because all directions forward in time converge toward the singularity. Outside the horizon, you can choose directions in space. You can move left, right, outward. Inside, outward is no longer a spatial choice. It becomes as inaccessible as moving backward in time. This is the deeper revelation. Near extreme gravity, space and time exchange roles. Far from massive objects, time feels like the inexorable direction you move through, while space feels navigable. But in the intense curvature near a black hole, the coordinate that once represented radial distance begins to behave like time. Moving inward is not a choice in space. It is your unavoidable future. From the outside observer's frame, as an object approaches the event horizon, the gravitational time dilation becomes enormous. Signals emitted from the infalling object take longer and longer to arrive. Each photon must climb out of deeper curvature, losing energy, stretching in wavelength. Light itself struggles against geometry. The phrase light trapped in time becomes literal here. Photons emitted near the horizon can orbit briefly, trapped in unstable circular paths. Closer still, even those paths collapse inward. The escape velocity exceeds light speed, not because light slows down, but because spacetime itself tilts inward so sharply that every forward, directed light path leads deeper into the hole. To an external observer, it appears that light from the infalling object freezes at the threshold. The object becomes a faint, lingering echo of itself, suspended at the boundary. But the true story is stranger. The event horizon is not a solid surface. It is a geometric boundary defined by causality. Beyond it, events cannot influence distant observers. Signals cannot propagate outward. When you see the infalling object frozen, what you are really seeing is the limit of causal communication. The image you receive corresponds to photons emitted earlier and earlier along the object's descent, each one increasingly redshifted and delayed. Time dilation here approaches infinity in the external description. Now consider what this means for the concept of time itself. If from one frame time at the edge seems to stop, while from another frame it continues, then stopping time is not an absolute statement. It is relative to an observer's world line. This destroys the naive picture of a universal ticking clock even more dramatically than high-speed travel did. Near a black hole, simultaneity fractures completely. Events that the falling observer experiences within moments may correspond to immense spans of external time. The outside universe races ahead, while the falling observer crosses the horizon in finite personal duration. Entire civilizations could rise and fall outside, while someone nearing the horizon appears nearly frozen to distant eyes. What appears as eternal suspension from afar is ordinary progression locally, but the geometry goes deeper still. At the horizon, light cones, those structures defining possible future directions, tilt inward. The cone's outward edge aligns with the horizon itself. Inside, all future directions aim toward the singularity. In that sense, the singularity is not simply a place in space. It is a moment in time for anything that crosses the horizon. You cannot avoid it any more than you can avoid tomorrow. This inversion reveals that space and time are not independent stages on which events play out. They are coordinates whose roles depend on curvature. The freezing illusion seen from afar is a consequence of the infinite redshift at the horizon. Each successive photon emitted as the object descends takes exponentially longer to escape, its energy diluted by the stretching fabric of spacetime. The object does not pause in its own experience. It continues inward, yet its ability to send signals outward diminishes towards zero. Time from the outside becomes stretched into near eternity at the threshold. This has profound implications for information. If signals from near the horizon become infinitely delayed, does information ever truly cross from the outside perspective? Or does it remain encoded at the boundary, smeared across the horizon in subtle quantum correlations? Modern theoretical physics suggests that the horizon behaves as a kind of storage surface, encoding information about infalling matter. The geometry might translate volume into surface description, transforming three-dimensional dynamics into two-dimensional encoding. If so, the apparent freezing of objects at the horizon is not mere illusion. It hints that reality might reorganize information at extreme curvature. Light defines the horizon, The boundary is drawn where even light cannot maintain outward direction. Time, at that edge, becomes ambiguous. For one observer, the infalling object never quite arrives. For the other, arrival is inevitable and swift. Both descriptions are valid within their frames. This duality forces a deeper question. If time can appear frozen in one description and continuous in another, what does happening truly mean? An event's reality depends on causal connectivity. Once the horizon separates observers, they inhabit disconnected causal regions. Thus, light near a black hole is not only trapped spatially, it is trapped temporally in the sense that its signals can no longer update the external universe beyond finite emission points. The black hole becomes a laboratory where time reveals its flexibility, not as metaphor, but as geometric fact. At the edge of extreme gravity, duration stretches, communication fractures, and the intuitive flow of moments dissolves into coordinate, dependent structure.